so I will just write on the blackboard. So please move forward. It's okay if you now stand up and come closer because the lights are not perfect, so they are a bit dark. And also, I'm not able to use this one because it's somehow broken. Okay, so please do come closer. Okay, and feel free to stop me anytime and ask questions. And yeah, maybe you do. I think you can just shout, and you don't have to raise your hands if you will not. But I will stop you if it's a problem.
And write on the board using big letters.
Yeah, I will try to hear you. Okay, and then
even if we don't shout, it's okay because so we can even hear the bottom of the room from the top from the start because you have to microphone.
Okay, so the mic, yeah. And okay, so this lecture will be the plan. So Frederick asked me to talk about the categorical theory of type theories. So what is a type theory, to answer this question in a mathematical way? And so I ended up talking, or the plan was to talk about SOGATs. So second order generalized algebraic theories. Okay, so that will be our definition of type theory. And yeah, so there are lecture notes. So there are lecture notes available through the school website. So if you click on my name, then there's a link to the lecture notes, which are not yet completely finished, but I will say excerpt of the lecture notes because it's too much. And there are lots of examples and lots of exercises there. So if you want to understand things more, then go through all the exercises. Okay, we will only do a few here. And I guess there won't be an so I don't know what's so there's no separate exercise session, but we can also do one if you want. So if you have questions, you can come up to me after the it would be nice to have some separate like exercise session as well, but okay.
During the happy hour.
Yeah, or there's happy hour and stuff like that. Okay, and then this will be the structure. So today I will talk about GOTS without the SO. Okay, and talk about the main content is what does it mean, what does derivability mean, and what does admissibility mean. Okay. Derivable and admissible, things that these Andre already said these words. Then the next lecture, the plan is to talk about only derivability in SOGATs. So to talk in a way that we can only talk about derivable properties, which is quite a lot already. Okay, then I will introduce how to translate SOGATs into GOTS. And because for GOTS we know how to talk about admissibility, we also know how to talk about admissibility for SOGATs as well, because we can translate and then we know what admissibility means. Okay, then I will have a separate, I mean, this is the plan that in the end we will do admissibility in SOGATs, which uses this translation but gives you much nicer way to do admissibility. Okay. But before I start with number one, I wanted to show you this this tower of abstractions to relate this talk to the other talks. Okay, so yeah.
So today we are also going to learn about derivability for GATS, and so since we know how to translate SOGATs into GAT, why is there a lecture about derivability in SOGATs?
Because this is just a pedagogical way of first talking about SOGADs and only derivability, and we don't want to talk in the codomain of the translation, because the SOGADs are really nice, okay? They are very beautiful and concise descriptions of languages. Once you translate them into GODs, what the result is not that nice. So maybe you don't want to be there. That's the short answer, okay? But we'll see. Okay, but to put this in context, so what is a language, or programming language or language? You could say that, well, things in the language or programs in the language are just strings. Okay, any string is a program, but then okay, then there are some strings which don't really make sense as programs. Then there are lots of different ways to represent the same program as a string. So you want to, so you can say, like, okay, I can describe which strings are the meaningful programs, right? You could define a predicate on strings inductively or something like this, but that we don't like to do. Instead, we go one level higher in the abstraction tower and say that no, a program is not a string. A program is a sequence of lexical elements. Okay, list lexical elements. And actually, we know how to translate strings into lists of lexical elements. And this translation sometimes fails, right? Some strings don't. And maybe you wrote some lexical element which is not in your language, then the translation fails and you don't get a list of lexical elements. And we also know how to print the list of lexical elements and that's not pasting. So, right, this translation is called lexing. This translation is called printing, or adding spaces. Right? That's spaces. That's the mathematical content of this. Okay, but then you can say, oh, not all some lexical elements make sense, because sometimes maybe you're like plus operator and you want to make sure that it gets exactly 2 arguments, or some list of lexical elements are not well bracketed. So then the solution is to define a predicate on list of lexical elements which are nice, right? No, that's not what we do. Instead, we define our programs as abstract syntax trees, and this, everyone knows that this is called parsing, and you can also like add brackets, right? Add brackets to the AST, and then you get a list of lexical elements, right? A well bracketed one, and this can also pair, just like this step. Okay, so in fact, that's very popular to say that the program is a list. It's an AST rather than a list of lexical elements. Okay, but then even for ASTs, most people stop here. But even for ASTs, there are some. Maybe they have some variables which are not in scope of a binder. Then you want abstract binding trees, well-scoped abstract syntax trees, and this is called scope checking, which can again fail. You can also turn for like here when you go from APT to AST, you invent names for variables. Okay. And actually, so when you go up here, you see you don't only like throw out some stuff. So if you go higher, there's less stuff. There's always a quotient happening as well. So lots of different strings correspond to the same lexical element. So maybe here I should write that in this step, the quotient thing is removing spaces, right? Or forgetting number of spaces. That's the quotient which happens, right? So forgetting the number of spaces. Okay, that's what's happening here. What happens here? You forget about the unnecessary brackets, right? There are lots of different ways to bracket the same expression. So here it's it's you basically quotient by some kind of bracket stuff. Okay, when you go up here, you quotient by alpha naming. Okay, this even has a proper name. Okay, that's the quotient here. Then you can go higher and say that not all APTs make sense because you want well-typed syntax trees, and this is called type checking or type inference. Okay, which can also fail. I don't know. This is also some kind of printing, or no? I don't know. This is easy here. There's not much interesting content. Okay. Here there's no quotienting happening. Here we really just throw out stuff, right? When we do type checking, yeah.
In a real implementation, these two will tend to be of different data types. So it's not literally an inclusion.
Yeah. But so there's no interesting.
Nobody ever implements the other direction. Well, you can maybe implement the other directions.
Yeah.
There might be reasons for that.
Yeah. Okay. And then you can go higher by saying that you have well-typed and quotiented. So here, quotiented. So here you, for example, here you have the program 1 + 1 and 2. They are separate. But here they are the same. So here you quotient by your semantic equality or your conversion rule or definitional equality or rewriting. So here this is only a quotienting. So you quotient by beta, say. Here you quotient it by alpha, here you quotient by beta or eta or whatever rules you have in your theory. And well, you can't really go down here because here this is already quotiented, so you cannot define functions which break the quotient, right? When you go down. So the only way to go down is if you know if your programming language already has normalization. Okay, then you can go down and pick out one unquoted well-typed term. So this is normalization. Okay. And then there's lots of confusion when people don't say which level they are working on. So Fred's lectures were given at this level of abstraction. And then he said, okay, I have these, or maybe this one or this one, depending on how you see it, because he said, okay, I don't care about alpha renaming much. So what he did is like, you define your language as ABTs, and then you define this type relation, which basically carves out the well-type stuff from this. And then you also define some conversion relation or rewriting relation, which basically gives you the data here. So this is the approach which is called extrinsic. Okay, so extrinsic, the real hardcore extrinsic people even start with good add numbers down here rather than strings, and then they say which good add numbers correspond to a correct, well-formed, well-typed, whatever, and they define lots of complicated relations on them. But now we will be in a very convenient position because we go as high as possible. We don't care about all the rest of the stuff. Yes?
Maybe it's a strange point, but is there anything you can say about the process of how you're going up? Because every time you're doing something, but you're like adding some information. Because for the lexing stage, you need to know how to lex the string and into which list you're getting. And then when you're doing the type checking, you need to know what type system you're working with and what base types are and all of that kind of stuff.
So this lecture's viewpoint is that the language or the essence of the language is this definition. And all of this stuff underneath should be basically automatically generated from this definition. There are lots of ad hoc steps because when maybe you want some convenient, fancy, surface language notation to write down things in a concise way, which we use all the time. So you add some cleverness when you define it. But the essence is up here, and basically you should be able to turn a handle and get all the stuff which is below it automatically, and then you can adjust it according to your needs. But I mean, in practice, we are really, really far away from being able to do this. Okay, in the science hasn't progressed that far. Okay, but still, you can talk about languages in this nice abstract way, and that's what we will do here. Okay, and then so this is called extrinsic versus intrinsic. The basic. Sorry, maybe you should ask it first, and then I will say this.
No, I was going to ask you. You said, so we can think of this as language or something. Do you feel like the thing that's at the top there is a concept that accurately captures language.
Yes, I think so. So SOGAT, I think that's the nicest definition of language with binders. That's a general thing. Okay, and it doesn't capture all languages. So what SOGATs don't capture is substructural languages where variables don't behave in the usual way. So, for example, it doesn't directly capture linear type systems or modal type theories or modal languages. I mean, some modal languages are also SOGATs. Then there's work on things which were people believed to be modal. They were able to get a structural presentation, and that seems to be seen as a progress if you get something. If you like massage things until you get a SOGAT. But the nice thing here is that there's no. So when you go downwards, you have lots of ad hoc choices, like you use paranoid rules of Andre. So Andre talked about ABTs in an extrinsic way, because when you do an implementation, you need to go down here, right? So when Andre said that this is a term and terms are not equal, like the lambda xt applied to you and the leg binding, they are up here, they are equal. You can't see the difference here. But for type checking, as non-well typed terms, they are not the same. So when you are at this level of abstraction, so those people who don't agree, maybe they are just don't agree because they are talking about different things at different levels. So that's why I think it's important to keep this in mind. And so the other thing that people say is this extrinsic intrinsic distinction. So the main example here is that the extrinsic way is if you have list of A. Okay, that's an extrinsic presentation. Compare, and then you know, let's say you have some list XS, which is a list of types A, and then you know that its length is 3. Okay, length of XS is 3. This is extrinsic. Compared to that, the intrinsic is if you have already some kind of vector or arbitrary type, which is already indexed by the length. So here, the correctness or the typing information is there in the type already. That's the intrinsic approach, and the extrinsic is when you separate the program from the property. And saying that okay, I have ABTs which are given by some BNF grammar, something like this, and then you have typing rules and conversion rules separately on top of this. That's you see it's this style, and this being already up here and not here up there you can't even see the difference between 1 + 1 and 2. You can't even measure the height of the syntax tree because you are quotienting by semantic equality. So yeah. Okay, question?
I see the distinction that you're drawing with extrinsic and intrinsic, but and you say, oh, to separate the type from the property, but is being a list of things of type A not a property in and of itself?
Yeah, you can always go down. Yeah. So, but and then say that there is some sweet spot in the middle. Now we go to the extreme. Okay, that's what we will try out. And actually, I think that everything that most important properties of a type theory can be expressed at this highest level of abstraction and can be proven at this level of abstraction. And this is relatively new. So 15 years ago, we didn't know that normalization for type theory can be proven at this level of abstraction. We thought that you need to do have some rewriting relation to prove normalization. Now we know that we can do this level of abstraction. And I will illustrate this later. Okay, so we will be fully intrinsic. Any questions about this? So I can only use the bottom blackboard, so maybe I will just erase this part for now. And okay, and then we start with, sorry, I just check if there's something. Okay, and then what I want to say today, so we will talk about gods, and for a god, I want to teach you certain notions which make sense for any god. Okay, So there's the notion of model. Then once we have model, we can talk about derivability. So what does it mean that something is derivable? Then I will say what a morphism is. Then what is a dependent model? What is a dependent morphism? Then what is syntax? What is induction? Then I can say what is admissible. And then what is a normal form and normalization. Okay? So these are all things, except of the last two, all of these make sense for any God. Okay? And I will only show you examples of gods and what all these things are for those gods. And if you look at enough examples, you will see how to do it generically for any god. Okay? So let's start with actually we start with an art, okay? Without the G. So everyone's favorite art is monoids, right? So this is my notation. So actually how I say what a monoid is, I just define them by their models. So I say what a model of monoid is. So monoid is a theory. A model of monoid is also called an algebra, monoid algebra, or simply monoid. Okay. So you have a carrier set, then you have some binary operation, which I write as a dot, C, right? Functional programming style, we curried operation. Then you know that this operation is associative, so x times y it's the same as x times y times z. Bracketed this way. Then we have some u, which is an element. This is a nullary operation, and for this we also have two equations: left identity and right identity, ideal and IDR. So u times x is the same as x, and x times u is the same as x, right? So this is a monoid, and everyone has seen lots of monoids. So for example, we can choose C to be natural numbers and dot to be, let's write x dot y to be x plus y, and u to be 0. And we know that addition is associative, and the 0 plus anything is the same as anything. So this is indeed a monoid. Or, you know, we can choose the binary operation to be multiplication, then we are forced to choose u to be 1, right? And this is also another monoid. Or we can do some very basic monoid where we have the one element set, that's the carrier, right? And then x times y is just that single element. We don't even care what x implies, and it's also that single element. And this also satisfies associativity and left and right identity. Or you can proceed to be two elements set, booleans, and then x times y, maybe the conjunction, and then we are forced to take u to be true. Okay, I just write pt. Okay. Okay, this is all familiar to everyone. So these are the models. And then what derivable means derivable is some operation or some equation which holds in every model, okay? That you can construct in every model. So for example, we have the duplication operation, okay? Which takes x in C and returns in C, and it just says x times x, okay? This is a derivable operation in the theory of monoids. Not extremely interesting. Or a derivable equation is u times u times u is the same as, right? We can derive this equation by maybe using right identity here, and then you just get u times u, id right, and here I use maybe id left. There are lots of different ways to derive this equation. But this works in any monoid, right? In any model, in any monoid, you can do this because the only things I use when doing derivability is to use these operations, somehow combine them, and somehow combine the equations. Okay, so this is derivability.
And sorry, what is the thing that is derivable, or is this just informal for now and it'll become clear later? because when you say that dump is derivable, dump is itself a definition. So it's the thing on the right hand side of the equal sign, but it's also its type. It's also the name shouldn't matter. But
Yeah. So I only show you examples, but if you wanted to do this in Kokoragda, say, then how do you derivable stuff? You parameterize your module with a monoid model. Okay. You say here's a model, then you open the model, and whatever you do after that is all derivable stuff. You cannot not derivable things. So this would be, with this idea, you can give a formal definition of derivability.
okay, so I've seen this how it works in proof systems when you're actually doing this stuff, but I can talk about in your model, like in your formalism, what is derivability? What's the definition for derivability?
No, then keep it informal.
Okay, yeah.
Okay, then you also know about morphisms, right? So if you have M and N, which are models, then a morphism from N to N, morphism from M to N. We write it with the extreme notation that it has a C component, right? Which goes from Cm to Cn, right? It has a dot component, which says that if you have an xm and the ym in Cm, if I apply C to xm times in M ym, right, then it's the same C applied to xm, and then you do the times in M and C applied to ym. Okay? You've already seen this. I'm just fixing the notation here, and then you also have a U component of the morphism, which says that if you apply Cm to Um, then you get Un. Okay, everyone agrees with me. Okay, and now to some more interesting things. So I cannot move this, so I will just start erasing from the left. Okay. So what is a dependent model over M, which is a model over a model M? It has the same number of components as the model, and everything is indexed over the base model. So it has a C component. Okay. By the way, here you see, here I only listed 3 components, and I didn't give any component for the equations. Do you think this is always the case? Like, you never have to give a component for the equations. So we don't work, our meta theory is not homotopy. Type theory is just, our meta theory for these lectures is extensional type theory. Okay. So like we have UI and, but we use quotients. So, or you can formalize all of this in homotopy type theory where you only work with sets. You assume that everything is a set. Okay. So the question is there an algebraic theory? It actually has to be generalized, I guess, where the notion of morphism has to talk about some equality. I mean, there's no ASS component of the notion of morphism here. But could you imagine? Okay, I will ask this question later again. You can also look it up in the course notes, and then we can cheat. Okay, so what is a dependent model? So we have a dependent over M. We have a family of sets over the carrier of M. Okay. Then we have the binary operation, which does the following. If you have a member of C at some xm, okay, then you have a member of C at ym, then you get a member of C at x times my. This is also xm and ym. Okay. So here in this operation, you see this binary operation has 2 implicit arguments, so I implicitly quantified over xm and ym, like in curly brackets in Agda or something like that. And you see that, so in a way that the C is over the base C, the dot is over the base dot, right? It mentions it. And then let's see associativity. So associativity says that if you have some X, Y, and Z, which way? This way is the same as X, Y, Z this way. Where now this here I'm using very fancy implicit arguments because what is the type of X? The type of X is C at some XM. Okay, this is C at some Y. Okay, so what's wrong with this equation? Yeah, it's not well typed because, or is it? So what's the type of the thing? Let's just calculate the type here on this side. But I mean, when I say type, it's a meta set. Okay, this is not yet confusing because our object language is just monoids and not some type programming language, but it will very soon become a type programming language. Okay, so the type of this is C at ym times m z, right? Because all of these components, so this dot is this dot, and you see that the arguments of this dot are indexed over the base model. Okay, then the type of this is C of xm times m, and then this thing, right? So ym times m zm, and this is the other way. Okay, so the type of this thing, so this thing is in a different set to this thing. Yeah.
You said you were working in extension of type.
Yeah, but it's not a problem because we already know that M is a model, right? So it satisfies this equation. So just as dot depends on dot here, the associativity equation depends on associativity of the base model. Okay. And then similarly for the other components, so U is a C at UM, and then these equations also depend on the base things, but with this fancy implicit arguments notation, you write it the same. So should I write this out with fully explicit notation for understanding? Because now lots of faces seem a bit confused.
I don't understand why it's not a problem.
Why is
Not a problem.
it's not a problem? Oh, you don't understand why it's not a problem. Well, it is not a problem. Well, type check is because of ASFM. So here you write that this equality is justified by having ASSM applied implicitly to XM, YM, and ZM. Right? So this is the type of the left-hand side, and the right-hand side has this type, right? C of XM times M, YM times M, ZM. Okay, so you see that this thing has a different type to this thing, but these two types are equal because of ASSM, associativity in the base, right? So this component.
In the type for the multiplication operator, what's the x and the y with the subscript m's? What's the meaning of subscripting a variable with an m?
What's the type of XM and YM?
Yeah.
Okay, yeah. So the fully explicit type of multiplication is, okay, let me write it this way, that I start here. So multiplication takes implicitly an XM, an XM and the YM, which is in CM, okay? And then it takes a C at XM and the C at YM, and then returns a C at XM times YM.
And what's the type of C?
Previous.
But then it's used in its own type. You have C has type CM. What's CM? And then what's and then at the same time what's C
Yeah,
has M?
yeah. So the dependent model, the notion of dependent model only makes sense if you start with a base.
Okay.
Oh yeah. Yeah. So yeah. So this is okay. This is also some outsider category theory introduction, because in category theory you have objects in each category, and you are always confused in which category currently we are living in. And this is similar issue that, okay, here we have a notion of model component C dot ESS for models, for dependent models, for morphisms, and they are all the same. They are just called C.
Just to make sure that I'm following correctly, what we're doing right now is basically defining a new definition of what a model is in terms of dependence, which is different from the one we had before, in that now the ground set C, let's say, it's not in set, but it's taken some dependence like CM, which itself is also a model.
No, we are not defining a particular model, but just as there for monoids, there's a notion of model and notion of morphisms. There's another completely new notion, which is called dependent model. Okay, let me give you an example of dependent model let's say a dependent model over this one. Okay.
Excuse me.
Yeah.
Just before this, I don't quite understand the notion for multiplication in the morphism. The notation, sorry.
Okay, so what is confusing, I guess, is that C is now not, so C is a projection, right? From, on one hand, C is a projection for a model. For each model, C projects out its carrier. But C is also a new projection for morphisms, because for morphisms, C doesn't project out the carrier, it projects out the function from the carrier of one model to the other model. So this C refers to this particular C, okay? Another notation that people like is that you already give a name to the morphism. Right. So here, when I said model, what is a model? I didn't give a name to the model. I only started giving them names M and N later. But you could already start here by saying that the morphism is called F. Okay. And then the C component of F is this. Then the composition component of F says that F preserve this. So the CF component of F and so on. And I'm stressing this notation because if you start doing more complicated languages than this one, then you end up in horrible notation mess if you are not very principled. So we already start very principled from the very beginning, from algebraic theories, yeah? Sorry?
Is a functor is dependent model?
Dependent model is a functor.
The C.
Yeah, probably you can restructure it to be a functor, but I don't want to go in there. This is just something that if you look at the notion of model, you can pull out the notion of morphism, and similarly, you can pull out the notion of dependent model. Okay, and you've got it, yeah, okay. And then there's a notion of section. Okay, no, sorry, I wanted to give an example. So an example is where C takes a natural number and says, I don't know, vector of pool of n. Okay, and this is not a dependent model yet because I need to give all the operations. So I say that if I have two vectors, let's concatenate. Okay, and concatenation is associative. Okay, and this is over this one, right? So you see that this plus behaves as Frederick showed in the first lecture for arrays, that it's well tied with regard to this operation, right? And this is encoded by the notion of dependent model. Similarly, you with the empty vector, which is over 0, right? So this is the kind of dependency which the notion of dependent model captures. Question?
Yes. So then, in this new definition of dependent model, the C is the one that we see before. We're not talking at all about this one. All the C's that we see here.
Yeah, the C is local. I mean, yeah. So I see both for the notion, like maybe just as here, the C is for the F, which I'm defining. I could say this is for the D for the dependent model. All of these C are for this, but I'm using the other C because I'm implicitly quantifying over CMs. Right? Okay.
So intuitively, the notion of dependent model is saying, oh, if you have a model of monoid over here, we can have a model of, in this case, once again, it's saying it's a model of the monoids, but that depends on some other model.
Yes, exactly. It's like a model over a different another model indexed over another model. Okay. Yeah. Okay. And I will this. Okay, this will be clarified very soon, because then my next algebraic theory will be something where everyone knows dependent models and dependent morphisms. Okay, but let me just go through all the notions here. So a dependent morphism is like a morphism. Actually, I save space by. Oh, sorry, I don't save space. Dependent morphism. Which goes from a model M to a dependent model D over M, okay, is exactly like a morphism, but it's not a ordinary function, but a dependent function, okay? So C takes an XM in Cm and gives you a CD over XM, okay? It's just the generalization of this, which is dependent with exactly the same equations, okay? So we have this component which says that if I have a XM and a Y in Cm, okay, then I can apply this dependent function either to the multiplication operation applied to Xm and Ym, and then map them to the dependent model, or I can do them separately. I apply C to Xm, and then I apply C to Ym, and then I multiply them. Indeed, they are the same. It's really just a simple generalization of this. Okay. So now we are doing type theory or dependent types. We don't only have simple models, but also dependent models, and not simple morphisms, but dependent. Okay. Okay, and I needed all this done to be able to say what induction on monoids is. Okay. So I say that M has induction. If for every B, which is a dependent model over M, there is a dependent morphism of M2. Okay, so this is what induction means, that for any, so in this case, M is a base model, and M satisfies induction if I can go to any D from this M by some kind of C, and then C is called induction. Okay, so I give you an example of a, and okay, and then if M has induction, it is called syntax. Okay, so we have an algebraic theory, which is monoids, and the syntax of monoids is a particular monoid which satisfies induction. Like syntax is something that you can do induction over. Okay, and we can, and the things you can do, if oh yeah, so I can say what admissible is. Admissible is something that holds for the syntax and that you can put by induction, but it's not, it doesn't necessarily hold for every model. Okay, so let's do the example, nice example for monoids. I want to prove that the following property is admissible for the syntax of monoids, is that for every x, okay, for xm, sorry, for every x in the syntax, we will have that x is equal to u. Okay, so this property is not true in every monoid, right? That for all x is equal to u. This means that the monoids would be a bit boring, right? But we can prove that this property holds for the syntax. Okay, how do we prove this? So note that we haven't constructed the syntax in some clever way. We just said that the syntax is something that has induction. And induction just means that into every dependent model there is a dependent morphism. That's all we said. Okay. So let's prove that this holds for the syntax. And actually, the usual notation for syntax is that we call it I. Okay. So I is it's like big M, but it's I because another name for the syntax is the initial model. Okay, and that's an exercise that you can prove that initiality is the same as induction. We like induction more than initiality. So initiality just means that there is a unique morphism into any other model. Okay. Yeah.
Is co-induction also finality?
Yes.
Lovely.
Yeah. It's all very. You can dualize these lectures, I guess, and then you can talk about infinite languages. Yeah.
You dualize dependent model.
Well, you can always encode. So there's a stupid way to encode dependent model is nothing else but another model together with a morphism into base model. And this one you can dualize, but I don't know, maybe with cofibrations, you have some kind of the dual of dependent types, and then you can do something like this, but I don't know. Okay, so let's do a first introduction. So I will, how did we do induction? Well, we define dependent models, okay? So now we need to define a dependent model over the syntax, over I, or over some I, okay? So over some model has induction and we call this model I, okay? So this is what we are giving, okay? All of the components of the dependent model. We first give the CD and now M is I, okay? So okay, I just write it again. So C goes from Ci to Z. And then we say that C of X should be defined like this, X equals, okay? Even before we will complete the dependent model, but if I has induction, then that means that there's a dependent morphism from I into this model. Okay, so that means that we have induction which goes from Xi in Ci into C of Xi, where the C is what I just defined. So this is Xi equals Ui. Okay. So if I'm able to define this dependent model, then because I assume that the syntax has induction, I get this function, so I know that actually really all elements of the syntax are equal to Ui. Okay, and let's see if we can do this. So maybe let's do first the simple case. Let's define U, okay, the U component. So U has type C of Ui, right? Sorry, I put the I's here as well. These are all okay. So U has type C of Ui, and says C of Ui says that Ui is equal to Ui, right? So that's easy to prove, just reflexivity. Okay, so let's do composition. So composition has two arguments, right? Let's call it E, which says C of Xi. Okay, and then I compose it with E prime, which is C of Yi. Okay, then the result needs to be C of Xi composed in I Y. Okay, I just copied this definition. Yeah.
So in the new things that you've written in the second line, the first equals is like a definitional equal, or like
Yeah.
you're defining.
Yeah, this is the definition, and this is the equality meta type. Yeah. So I don't distinguish these because I'm working in extensional type theory. On paper, this is really nice. Yeah. Okay, so now I need from these two things I need to build this. Okay, but if I unfold the definitions, then what does E say? So E says this C of xi says that xi is equal to ui. Right? C of yi says that yi is equal to y. And here I need to prove that xi times yi is equal to ui. Right? This is what I need to prove. So that's easy, right? I just apply the two E and E prime, which I can call induction hypothesis for monoids. And then I get that this is the same as U times U. And then I apply left or right identity and I get that. Okay. So we did now, and by induction, we proved that in the syntax of monoids, every element is equal to U. Okay. So that also gives us a hint on how to implement the syntax of monoids. We can just pick the unit set, right? One element set, and then that works well as a syntax. Okay, but actually there's a generic way to construct syntaxes for algebraic theories, which works also for monoids, but works for everything else. So there's always a way to construct a syntax. So whenever you have an algebraic theory, you have a syntax, and for monoids, what you do is you just use binary trees. Right? You say that in a monoid can be built using dot or using U, right? These are the kind of binary trees that are the monoids, but there are too many binary trees because if you just take the syntax to be binary trees, then the equations are not satisfied. So you quotient by the equations. For example, associativity says that if you have a monoid like this, I don't know, A, B, C, then it is the same as this one, right? But here is the A, and here is the B, and here is the C. And then to construct all the syntax of monoids, you just take all these trees, which are generated by the two operators, the dot and the U, and then you quotient by the equations. Okay, and that's the syntax. And this works in general. Okay, so I think that's all I wanted to say about monoids. Any questions? Okay, then my next algebraic theory is even simpler than monoids, which might clarify why we call this induction and or why we introduce dependent models and dependent morphisms. So the next algebraic theory is PSE. So pointed set with an end of function, PSE. So a model is an N, which is a set, a Z in N, and an S, which is NR1. Okay? And let's review all the notions that we talked about there for this, this algebraic theory. I mean, this algebraic theory doesn't have any equations, so it's particularly simple. So this is the notion of model, pointed set with an end of function. Then the derivable things in this algebraic theory are very stupid, or there are no derivable equations, and the derivable operations are, I can iterate this operation, and that's it. Or I mean, I can use Z and iterate S a finite number of times. Those are the only things I can do, right? Then the notion of morphism is clear, right? So I have a from M to N. Oh, I shouldn't use N now. From M to O. Okay, I have an N which goes from N of M to N of O, right? Which preserves the Z, so that N applied to Zm is the same as Z of O, and also preserves S, so N applied to Sm of some Im is the same as SO applied to N of I. Okay? Now, what is independent? Well, so that's the point. So it's a dependent model over M. So I have an N, which is an NM arrow set. I have a Z, which says that N holds for Zm, and I have an S which says that it's n holds for IM, then n holds for S m of IM. Right? So the dependent model is really just a model where I always index over with the base components. Okay. And then induction says that if I have a I in n of I, then I have a m in D for some dependent model over IM. Okay, with two equations. Okay, and this is just the usual induction and natural numbers, right? So the dependent model is called the motives and methods of the dependent eliminator or the induction principle for natural numbers, and then induction is just induction. So, and this PSE is the notion of natural number algebras. Okay, so okay, and then the syntax. Okay, the PSE syntax is just natural numbers with 0 and +1. Right? This is the model, and we know that natural numbers support induction. So, okay. So maybe one subtlety is that here induction works for n. So this can be a set. This n doesn't need to be a proposition like in piano arithmetic. Here we have proof relevant induction. Okay, and then iteration or primitive recursion. Those are all special cases of the induction. Okay, induction is also called dependent elimination. Yes.
What about transfinite induction? Transfinite recursion?
Yeah, so for that you need a different algebraic theory. Okay, so that's not ESE, but something else. Okay, and then so for PSE, okay, we talked about all of this, but what are admissible things for PSE? So for PSE, the admissible things are, so the derivable things were really, really boring for PSE. The admissible things are all the things that you usually do when you study natural numbers in high school, like addition and multiplication, exponentiation, and the Ackermann function, and so on. These are all admissible properties of pointed set with end of function models. Okay, or actually they are admissible properties of the syntax of PSE, which is natural numbers. Okay, so in the previous, so for monoids, derivable stuff were kind of interesting, and admissible stuff were all completely boring because there was only like u was equal to nx, and here it's the opposite. Derivable things are really boring, and admissible stuff are interesting, and associativity of addition, and the fact that natural numbers form exponential semi-ring, or exponential rig, that's all admissible stuff. Okay. Okay, so now let's go to some nicer example. Okay, I want to give an example of a simple programming language, a very simple programming language which doesn't have variables. Okay, so I call this razor because there's the Hutton's razor programming language, and this is some variant of that. And this will be a first example of something which is not an art, but a GOT. Okay, so this is a GOT where some more interesting things happen. So in a GOT, you don't only have one set, but you have multiple sets which are indexed over each other. So first of all, this razor has a set of types. Okay, and then it has a set of terms which are indexed by types. So now I'm saying what a model is. Okay, this is a model. So there are types and terms. Well, in this very simple language, there are only two types, bool and okay. Those are the types. Then we have true and false, which are nullary operations, which return a bool. Then I have if then else, which takes a TM bool and a TMA and another TMA and returns a TMA. So here, this operation also has an implicit argument. Just like previously we saw that in the notion of dependent model, we used implicit arguments. Now, because now we are at GOTS, we already make ourselves nice notation by using implicit arguments already in the notion of model. Okay, then, oh yeah, we have some equations. So we have some eta1 equation, which says that if you apply eta to true and TNF, then we get the same as T. We have a beta2 where if you apply if then else to false and TNF, then you get F. Okay. Okay, and then we have some ways to include real natural numbers into terms of type not. And then we have some is0 operation, which goes from TM not to TM pool. Okay, and then we also have addition. Okay, addition, which takes two TM nots and returns a TM not. TM not. And then we have some more equations explaining how E0 acts on numeric 0 and how addition acts. Okay, but the addition one is interesting, so I write it down. So I have a plus beta, it says that if I apply num of n, and then the plus operation to num of m, then I get num of n plus m. Okay, so this is the notion of model. Okay, so here in the plus rule, I overload the plus, okay, because we have plus operation in our language, and also we have plus operation in our meta theory, so we can add natural numbers in our meta theory, and this is the usage of the meta theoretic plus, and this is the object theoretic plus, okay. So, and this is a very common thing that you have the same things in the object theory and meta theory, and you have to get familiar with this. That's why we overload the notation. Okay, and you see, so here you can also, and all of these notions that we discussed before make sense for this Razor language as well. I want to show you the derived, maybe, sorry, let's just go through them slowly. Derivable, what are the derivable things here in this language? So derivability is the same as what we call programming. Okay, programming. So the derivable operations are the programs. Okay, those are the things that in this language we can do programming with. Every program is a derivable operation, and then running a program. So operations are programs, and equations say how to run the program. Okay, run the program. That is derivability. Okay, so already if you have a language definition like this, when you only say the model, you can already do programming a language. Okay, and that's what we will also do for SOGATs at the next lecture, which will be much more interesting languages. Okay. Let me show you the morphism. The morphism is interesting. So what if I have M and N models? What is a morphism? So first of all, the morphism has a tie component because I need to map types in M into types in M. Okay. And what is the term component? Well, if I have a term in M of type AM, okay, so AM is now a type in M, then I need to be able to map this to a term in N. And what will be the type of the term? Well, it cannot be AM because that's an M type, and I need an N type. So I refer back to this tie equation. Okay, so this is tie of AM. Okay, So maybe I add the F indices, so the morphism. So F goes from M to N, morphism. Okay. Then the F operation for terms refers to the F operation on types. Okay. So this is this thing doesn't happen in ordinary algebra. This happens in generalized algebraic theories. This is also, I mean, maybe some people heard about induction or recursion. So this is this situation. Okay, and then we have notions of dependent model, dependent morphism, and syntax and induction the same way. So the admissible things will be the things that we can prove by induction on the syntax. Okay. Okay, so one basic example that we could do is normalization for this language, which is particularly simple. So we have a very simple model which we call standard model. Where I just fix types in this model to be set itself. Okay, so then this must be set 1. So this is a large model. Then terms of type A in this model are just elements of type A. Okay, and then bool is the meta-theoretic invariance. Okay, not is the meta-theoretic natural numbers. Right, this model makes sense because 2 has type set in the meta theory, and N also has type set. Okay, and then true is the TT, the meta-theoretic true, false is the meta-theoretic false, if then else is implemented by the meta-theoretic if then else, and so on. Okay, and all the equations are just all by definition in this standard model. Okay, and this okay, so I said that the okay, sorry, I should have said it before for the previous theory that so the syntax, right? The syntax has induction. But there is the special case of induction where the dependent model that you use is coming from an ordinary model, right? So whenever you can play around with these notions of model and dependent model, so whenever you have a model, you can turn it into a dependent model in a way that you just don't care about the indexing set, the base model, right? So for PSE, if you have a model like this, you can turn it into this by ignoring the input, right? So you can say n of, in the dependent model, n of anything is just n of some n, okay? And then z of d, you just define it as z of n, because this will then be just n. Okay. Same s of d, can just define it by s of n, because all these dependencies then don't matter, okay? And then if you do induction on a simple model, it is called iteration, okay? So syntax has induction, but syntax also has iteration. Iteration means that you have a iteration doesn't go into a dependent model, it's just a morphism into a model from the syntax. Okay, and in the case of programming languages, we call this interpreter or evaluator. Okay, so from this, for languages, we get interpreters or evaluator, I mean, and then interpretation into the standard model is called meta-circular interpretation, or what else? Oh, this is also called automorphism, right? So okay, so what I'm showing here, I mean, yeah, I'm just restructuring lots of existing stuff that you heard about, like induction and automorphism and fold. This is also called fold. Iteration is also called folding functional programming. In this abstract like algebraic setting where we only think about algebraic theories, and all of these things make sense for algebraic theories. They are just called differently in different parts of the world. You know, induction is also called structural induction, dependent elimination. Yeah. Okay. So I mean, this is nice because lots of different notions become the same. I mean, this is a general phenomenon when we study type theory, that there were all these separate notions, and then you simplify the world. So viewing the world through the lens of type theory is a simplification rather than making things more complicated. Maybe the common belief of people who study type theory is that the world is a nice place in some sense. Okay, so iteration into this model, that's called meta-circular interpretation, but actually for this Razor language, it also gives a normalizer. Okay, so what do we get if we iterate it into this model? Well, first of all, we get a morphism from tie of the syntax into tie of this model, which is set. Okay. This is the component of the morphism, which is this one, and I rename this component to n. Okay, this is the normal forms. Normal forms for a type are given by a set, and it makes a lot of sense that normal forms of bool I are meta-theoretic booleans, because there's only, in this language we have enough equations to show that actually there's only two elements of an F bool. Okay, and then normal forms of natural numbers, of not in this language, are just meta-theoretic natural numbers. Okay, and then we have the second component of this morphism, which we get from interpreting the syntax into the standard model, and we call it norm. Okay, for normalization. What does it do? Well, it takes a term I of some AI and returns a normal form of type A. Normal form at A, right? Why? Because terms of A are just A. So this set needs to be the same as this. Okay? So okay, and then we have all the equations which tell us how to normalize this language. So this is a particularly simple language in which the standard interpretation just normalizes it. Okay, and then the example of induction, the only interesting example of induction that we can do on this language is to show completeness for this normalization, okay, for this normalizer function. So we can show that TMI of AI is, I mean, normalization goes to NF of AI, right? This is the function. Okay. We can define the function in the other direction. We can just map meta-theoretic booleans to object-theoretic booleans, meta-theoretic natural numbers to object-theoretic natural numbers. And then we can show that if you do a round trip, so if you take a term, normalize it, then you map it back, then you will get something equal. This is called completeness of normalization. And you can do this by induction on this syntax. Okay, that's a very nice exercise. And then there's the other round trip, which we call usually stability of normalization. So stability means that you don't have, that if you start with a normal form, then you map it back into a term, and then you normalize it, you get back the same normal form. Okay, so together with all of the completeness and stability, say that syntactic terms, so terms in the model I, which is the syntax, are isomorphic to normal forms. Okay, this is like full normalization. And then for practical purposes, usually completeness is enough. So, and I mean, this is, so in this the previous languages were very boring for normalization, but here is more interesting because the normal forms are really simpler, right? So here the syntax, you can also draw them by trees, which are built in a well-typed way, where, for example, this rule really makes sure that if then else, the two subtrees of if then else have type TMA for some particular A, okay? And these trees are built in this nice way, and then you quotient them by all of these equations, and because the equations might have been given in a stupid way, you can you need to do some actual work to show that to show completeness and stability of normalization. Okay, and then so what we usually get, so what there's also no formal definition of normal forms that we will give or in the course notes, but normal forms are usually have some I mean, the best way, we want normal forms to have decidable equality, or at least it should be easier to decide equality in normal forms than in ordinary terms. So that's what we usually do. If we want to decide equality of terms, we map them into normal forms by interpretation into some model. Then we can check equality of normal forms, and if we have completeness, then we can also decide equality of terms. Okay, stability is not needed for deciding equality in the method theory. Oh, sorry, in the object theory that we are looking at. Why is stability good? When do you want? What do you gain from proving stability for a language? Okay. Why would you want stability? In the answer is that if we, so normal forms are some simpler because they are isomorphic. Once you have completeness and stability, then they are some kind of simpler representation of the language. So you can get a nicer induction principle for your language. So once you prove normalization and you want to prove something about all of your terms, then you don't have, if you prove normalization, then you can prove the other properties of your terms by just doing induction on normal forms. Okay. So basically anything that can be proven about this language, you can just prove it for meta-theoretic natural numbers and Booleans. Okay. Whatever you can do in this language, you can just do with natural numbers and Booleans. Okay. So stability makes it sure that you don't have to care about the language is all the stuff that you can write in the language, all these operators and equations. They are not interesting because you can just replace them by natural numbers and Booleans. In the model of normal forms is the same. Yeah.
Why would I want to do that? Probably, I have a programming language. I have some algebraic data type. It's my programming language. I can do my proof by induction on the syntactic structure of my program.
Yeah.
And I have to make a case for each rule in my judgment. But I could do some other proof about natural numbers and Booleans instead, but it would be much harder for me to understand what it means. But that's like a
usually normal forms are much simpler than your original programming language. So you look here. So our original programming language has these lots of rules, lots of maybe complicated rules. We can't even see what's going on. But then you replace them with some much simpler structure, natural numbers, and Booleans, which are like if you write down the inductive definition of natural numbers and Booleans, it's like 4 lines or 5 lines. 4 lines, right? There's true, false, 0, and successor, and that's it. So 4 lines are much simpler than all of these things. And then, I mean, this is a new, so you get a new induction principle. Actually, even this normalization even makes sense for languages where there are, for example, you could have, there are languages where every term is equal. Okay. You have equality, you don't care about the content in terms, you only want to know whether there's a term or there doesn't exist a term. For example, first order logic is a language where you have the language of proofs and you don't care which proof you meant. You don't have equation, you have one equation for a proof that any two proofs are equal. Okay, and even for first order logic, it makes sense to normalize proofs, to prove normalization for proofs, because then you have a very nice induction principle for proofs. For example, to prove that in intuitionistic logic, the law of excluded middle cannot be proven, it cannot be derived, that's the easiest way is to prove normalization for proofs in first order logic. And then you can analyze the normal forms and directly see that the law of excluded middle cannot be proven. Yes?
An easier way is to give a model in which excluded middle doesn't hold, just a hiding algebra on 3 points.
Yeah, that's yeah, so one of them is syntactic way maybe, but even this way of presenting normalization through going into some model, it's also a model construction essentially.
I think algebras for proofs.
Yeah, no, this also makes sense for propositional logic. But so no, this was just an example where proofs are uninterested. I mean, so normalization is not about obtaining the normal form, which and then you can decide. Or sorry, no. So this example was another use of normalization, which is not decidability of equality, because that's or running a program, because we don't want to run proofs because there's no interesting content. We only want to know whether there's a proof or not, but it's still useful to get normalization. Yeah. So, okay. And then the next language that I wanted to show is, I won't have time for this, so this will be postponed to the next lecture, I guess, is a simply typed combinatory calculus, which is still a GOT, and still doesn't have variables. Yeah.
So can I hope to generalize my proofs with a dependent model such that I only need to maintain normalization, and then my remaining theorems will fall out of it? If I sort of, okay, I have a programming language, but I'm changing it all the time because I'm sort of designing it, right?
Yeah.
And then I have a proof of normalization, or I have some representation of normalization, and then I've done the theorems I want in my dependent model or about Booleans and natural numbers. Can I hope that if I only maintain the code that does normalization, then I don't have to maintain these theorems? I can change my language all I want, so long as I maintain normalization, I get the theorems free.
Yeah, so I guess this is an application. Yeah, so this is an application where instead of doing, so you say that I'm changing my language, but I don't change my normal forms, or I don't intend to change my normal forms. Then I add some stuff to my language, and what the things that I prove about my language, I don't prove directly by induction on the syntax, but I prove them by induction on normal forms directly.
Exactly.
And then this could be an application that you add new stuff to your language, and you always maintain just normalization. The components, what do you maintain? You maintain the components in your dependent model over the syntax, right? Normalization is, the content is a dependent model. So you have one single dependent model that you want to maintain, and that's a good application. Yeah.
I have a very basic question. So I think I understand just all this, but I don't quite get what a GOT is. It's like all this wrapped together.
Okay.
GOT is an algebra, and all the modules of the algebra, and all the derivable theorems of the algebra.
Yeah. Very good question. So the question was, what is a GOT? Whether the GOT is all this stuff. So no, so I gave now like 3 or 4 examples of GOTs, right? So the first GOT was monoids, that's a GOT. Then pointy sets with the Dendo function, and then razor, that's also a GOT. Okay, so that's a generalized algebraic theory, and the GOT is determined by the notion of model. Okay, so once you say what a model is, you already know all the rest. Okay, so this is why for razor, I basically only said what a model is. Okay, and then I said that you can imagine, you can extract from the notion of model all the other stuff, the morphism, dependent model, dependent morphism, syntax, and so on. Okay, and I didn't say what exactly is allowed when you write down a GOT. Okay, so like I said that I define some sets, and then some which are the carriers, then some operations, and then some equations. Okay, and that's the GOT, but there are some restrictions. So for example, I cannot define an operation which returns not in one of the sets, but in, say, meta-theoretic nature. That's not allowed. Then there are, or higher order operations are not allowed. But yeah, okay. And then at the, we will give a definition of what a GOT is in the next lecture.
Basically, it's a specific kind of algebra. It's certain characteristic.
Yeah, yeah. But whatever is algebraic is yeah. So in algebra studies, things which are algebraic, and those are the same as GOTs. Yeah. Yeah. Okay. So let's go for copy paste.